Let's now find all fifth roots of negative 12 plus 5i, and then we will find the definition of negative 12 plus 5i to the 1/5 power. Um, so let's draw the picture for this. So negative 12 plus 5i will be over here in the complex plane. We need to convert this into trigonometric form. So the distance from the origin is 13. And the angle here, theta, has to satisfy that tangent of theta is equal to negative b over a, which would be, in our case, negative 5/12. So the simple-minded thing to do would be just simply take the arctangent of both sides, arctangent of negative 5/12. That would be the obvious answer. Unfortunately, in this case, it is the incorrect answer because the angle is in the wrong quadrant. Arctangent of negative 5/12 is going to be down in the fourth quadrant. And so I need to add something. I need to add pi in order to get an angle that is in the correct quadrant, in the second quadrant. And I'll let you think about this, but using trigonometry we can show that the angle theta is also equal to the arc cosine of negative 12/13. And that requires no adjustment because arc cosine takes values between 0 and plus pi. Okay, so in our case, we're going to try to solve the equation z to the fifth is equal to negative 12 plus 5i. Now this is a fifth degree equation, and so there will be 5 different answers. The form of the 5 answers will let z be equal to r times e to the I theta, so that the right-hand side, or sorry, the left-hand side becomes r to the fifth times e to the 5i theta. And we remember that 5i theta is cosine 5 theta plus I sine 5 theta. On the left-hand side, we have 13 times e to the I, and perhaps I should use a different Greek letter on the left-hand side. So I'm going to use theta for z, and for the angle here, I will just choose some different Greek letter. Let me just choose alpha. So e to the I alpha, where alpha is equal to the arc cosine of negative 12/13, or else the arctangent of negative 5/12 plus pi. They mean the exact same thing. So in our case, for this to happen, we need that r to the fifth is equal to 13, and simultaneously we need to have that 5 theta is equal to alpha plus 2 pi n. Now the r to the fifth equals 13 part, that's fairly self-explanatory. The second part, let me explain where that comes from. Remember that e to the I 5i theta is cosine 5 theta plus I sine 5 theta. And this part has to be equal to e to the I alpha, which is cosine of alpha, plus I sine alpha. So the two cosine terms have to agree, and also the two sine terms have to agree. That doesn't mean that the angles themselves are going to be equal, but it does mean that the angles are going to have to be coterminal. So 5 theta doesn't necessarily have to be equal to alpha, but the difference between 5 theta and alpha must be some integer multiple of pi. And so that's why we have the expression 5 theta is equal to alpha plus 2 pi n, because 5 theta and alpha must be coterminal. So solving for r, we get that r is equal to the fifth root of 13. That's the modulus of z. And the angle has to be equal to alpha over 5 plus 2 pi n over 5, where n takes values between 0 and 4. So there are going to be 4 different angles, or 5 different values of theta, and hence 5 different solutions. Okay, so let's plug in the first, n equals 0. If n equals 0, that gives that z is equal to the fifth root of 13 times the cosine of 1/5 times the arc cosine of negative 12/13 plus I sine times 1/5 times the arc cosine of negative 12/13. And so this fairly long expression will be the answer for the first fifth root of z. And furthermore, that is the answer to the second part of the question, negative 12 plus 5i to the 1/5. Whatever you get when n equals 0 when doing this computation is going to be negative 12 plus 5i to that exponent. It's called the principal root for the expression. Now the other terms will have kind of the same form as what we have before. The first root, n equals 1, will be that z is equal to the 13th root of 5 times the cosine of 1/5 times the arc cosine of negative 12/13. And then I need to add 2 pi times 1 over 5. Then next would be the same thing, I times the sine of the exact same angle, 1/5 arc cosine of negative 12/13 plus the same angle, 2 pi over 5. So that's the n equals 1 case. The n equals 2 case and n equals 3 and n equals 4 will be very similar indeed. So let me just copy what we just did for the n equals 1 case. And of course the difference will be that because n is equal to 2 instead of n equals 1, we change the 2 pi in both places to 4 pi. And by now hopefully you can guess what's going to happen for n equals 3 and n equals 4. So let me clear some space so that we have room to put this. And let me bring this up higher. So the n equals 2 case, let me copy that. And I'll just simply paste it twice. First off, for the n equals 3 case, the angle will now be increased from 4 pi over 5 to 6 pi over 5. And then for the n equals 4 case, the angle will change now to 8 pi over 5. And if I go to n equals 5, I'd have 10 pi over 5, which is 2 pi, which cycles back to the first answer that we had in orange. So those are the 5 different roots, and then it's just simply a matter of carefully plugging into a calculator to evaluate these expressions. So there's nothing conceptually difficult about it other than just simply doing the work of plugging into the calculator. So anyway, those are the 5/5 roots of negative 12 plus 5i without simplification into a calculator. The one in orange is the definition of negative 12 plus 5i to the 1/5 power.